Welcome, welcome. Today is going to be the third day, third lesson, third study session towards our little AI engineering project. Last day we went over some basic setup, set up PyTorch. So this included Torch, Torch Vision, and I want to say, if I'm not mistaken, a video Torch and Torch Vision. Torch Vision was for video parsing, and Torch just being the overarching structure. So we got those installed into our virtual environment, which we uh, named the env, and then we activated and or we sourced the activate inside of here to have it be taken into effect, as you can see. So all the packages and libraries that we install will be inside of this virtual environment. So where are we now? Ingesting the video, right? At the core of everything we're trying to accomplish, this is going to be first. We went over tensors, pretty in depth last video. So if there's anything you need as far as tensor information, it's all there. And from my understanding now, we're going to look to take one of our videos. This is this sample that we have. We're going to take one of our videos and produce the start point. Let's get some controls here to be able to get the start point, the end point, and then specify based on the patterns that are recognized here who is the receiver, who is the quarterback. All right. And from my understanding of tensors, what's most likely going to happen and kind of the convolution layers, it could be a multitude of things. But for instance, and again, this is just my understanding. I can't emphasize or stress this enough. I might be wrong, right? And I might come into the future to understand that my understanding now is not correct, but the transparency and the visibility of the thought process that's going on. The tensor, in a way, is going to find somehow, some way, a pattern to decipher the fact that this is a receiver and to decipher the fact that this is a cornerback. So, one common trait between receivers and cornerbacks are their stance. Now, I'm not going to specify or define exactly what stance a cornerback should be in and what stance a receiver should be in, but what will happen is there will come to be maybe uh, more horizontal segments are found within the cornerback because normally they're hunched over, which will make them more square in appearance, right? Where a receiver is normally further straight up. So, would this not be a common between all routes, all possessions? Maybe, maybe not, but that is my understanding of what we're trying to accomplish next. So, determine the start. So, how do we determine the start of a video? How? And then where or what do we do? Place info. Right. So this how is most important to me right now at this moment. How? How do we determine the start point of a video? And let's define start, right? Beginning of movement. The start that we're looking for isn't the actual start 0001 of the video. This doesn't matter, right? What we care about is that this right here then kicks off the understanding that we said before. How quickly does he get up the field? Pretty quickly, right? So from 6 seconds to 8 seconds is what we want to care about. So, how do we find motion? Or essentially, again, working off my understanding, what we're going to do is we're going to have clips with tag start times. Receiver. Okay. And then we are going to allow AI to try and decide on its own and check against tag clips, which will then allow it to come to its own capability, understanding of how to determine the start times from here on out. Now, because of this, though, this means we need to be able to first determine who the receiver is. Without knowing who the receiver is, how can we know when the beginning of the movement of the receiver happens, right? Because if the cornerback is moving back and forth, we don't really care about that. We care about when the receiver decides to move because that is technically the start of the play. Okay. So, first things first is we need to determine, and let's generalize this, right? Determine an object and a still picture. Are we not? From 0, 0 of the clip, we want to know who the receiver is and who the cornerback is without any other clues. Simply a picture and one moment at a time and move on from there. So, now that we've broken things down to the very core principle, how can we do this? All right, that's next. Well, how to differentiate. Let's do this actually. Mhm. All right. How do I start making? Oh, so what we're gonna do is start with something that's actually not even related to this, right? We are going to first figure out a way to determine between apples and oranges, right? So, F image with the loss that punishes me wrong. Sounds good. Input, red, green, blue image, 2224 by 224 pixels. Output. So, as we always do, right? What is this exactly? All right, what is a logic and what is a softmax? Ah, I actually have changed my personalization settings to ChatGPT, and I have it quizzing me now. Actually, whenever I ask a question, unnormalized score output by a model for each class before converting to probabilities. Okay, it is not a probability. Relative discuss arbitrary nonlinear. Logics are the inputs to softmax, and then softmax is converts logics into positive numbers and normalizes them to sum to one. What's the operation side softmax that makes step one happen? And it's a absolute, right? Six. Um, did it not say converts logics into positive numbers? What's the operation inside the softmax that makes step one happen? E to the zi negative would be. Ah, I see. So it maintains the fact that it's technically negative, but it converts it to positive. So it's a logic zi applies to the zi. E of x is greater than 0 for all real x. Against these positive. This is logic. Okay. So it sounds like this looks like it's going deep into the math of it. So let's pause right here for 1 second and try to circle back around to what we're doing here. So essentially, there are numerical functions that feed into the probability between the two, and loss is cross entropy between predicted distribution and true label. So if it's 90% an apple and it is an apple, then you have a loss maybe of 10%, right? Does it work that way? I said 10%. Wait, loss is not 100% predicted. True class is apple and the model output is p. Apple equals 90. All right, all right. Okay, the model predicts. And then, okay. When the model gets extremely confident but wrong, 1 minus p barely changes, but negative log of p explodes. The model predicts the true label is apple. I see. So when you're very wrong about it being an apple, it gets penalized heavily for it. So it's 50% an apple, 50% an orange, and the true label is apple. Which loss is bigger? Um, if you were at 90% correct, then the loss would be bigger because wait, the model predicts. I'm gonna go A, right? I don't know. Let's really think this out, right? Apple, orange. If an apple prediction is 50%, orange prediction is 50%. Loss at 90% correct. What does 90% correct mean? So what does loss at 90%? Right? Let's think about it before we even ask. Loss at 90% correct, loss at 50% correct. What is the percentage of correct, right? Um, is it how right? It's not how right the AI feels it is because this is the prediction here. And so yeah, I really don't know. Okay, so it's completely disregarded. Wait, no, it's not. The model predicts 50%, and the true label is Apple. The model predicted 90% probability for the correct class. Loss equals negative p correct, which is 90. I see. Loss at 90% correct. I see. I see what you're saying. Loss at 90% correct versus loss at 50% correct. So your loss at 90% probability and you're correct, or your loss at 50% probability and you're correct. So the loss at 50% would be greater because you need to be, just logically speaking, you need to be penalized if you're only 50% sure, but you're right. Right? You still need to be penalized for that. But if you're 90% sure and you're right, then the loss is going to be less. It's my understanding. Um, I don't really, right? I don't have a calculator, so not very. Let's let's be cheeky, right? 69.69, 0.69. So 69% loss versus 10% loss, or whatever, whatever. Okay. So this is around where that log point 0.5 would be if you're about 50% sure, and then once you get, yeah, okay, gotcha. Can you calculate log? I'm so tempted to actually spend time here and kind of go over learning logs. Um, well, if anything, remembering them. No, I've definitely used them before in class. Let's let's hold off and let's head back over here real quick. So now we understand loss, and this is what I mean, right? We went looked at logits and softmax and understand how they're vectors that work with probabilities. Do we really understand them in depth? No, but that's okay. Same with loss. Do we really truly understand loss super in depth? No, but we understand now that there's going to be a true label and you're going to predict with a certain amount of confidence. If you're right in that true label, um, the loss is kind of tracking your score, for lack of a better word, between your confidence and you being right or wrong. Can this setup train? If there's no label, how can you train? No, because it's going to guess, but it won't be able to be corrected through loss. Correct me if I'm wrong, though, while that loads. Let's see what's next. So we're going to need a minimal labeled data set. Right. You know what? What if we treat this exactly like wide receivers and cornerbacks actually? Collect 100 images of apples and oranges. Ideally 1,000 plus each. Okay, let's let's do this. Let's do this. Let's do this actually. Well, wait. Let's see if there's an answer. Yes, if there's no label, the supervised setup cannot train. There's no laws, so no gradients, no weight updates. Perfect. No filters, never specialized, and we understand filters are to be the pattern matching of, oh, this looks relevant to this, that, and a third, to be able to then kind of put all the patterns together and say with confidence that this is 50% an apple based off these patterns, whether it's the edges, whether it's kind of the whole layer, the colors, the pixels, whatever the case may be. Um, okay. One second. Um, all right. So, if we're really gonna start, I mean, getting the labels and everything, let's just go ahead and do it, man. Let's go ahead and start with, let's swap from oranges. Yeah, yeah, yeah. This is it. I mean, this is exactly what we need, right? So first, we're going to train on the difference between a wide receiver and a cornerback. Right? We're gonna get all different types of pictures of wide receivers and cornerbacks to put into the AI. Fill in the three blanks. Blank one in step three. Predictions. Mm. You compute the loss using cross entropy predictions, and this is your label, right? The true label. So true label. Blank two and step four. What kind of internal patterns get reinforced? Gradient descent strengthens internal that. Don't know. What would that be? All right, gradient descent. So let's look for gradient descent here. Gradient descent. This was the true label. Led to lower laws get reinforced, right? We want the lowest laws possible. So for that, gradient descent strengthens internal filters that lower the loss, in my opinion, right? Over many examples, the network becomes good at predicting whether a frozen frame contains a receiver or a cornerback because it has learned uh, that repeatedly reduced loss on the labeled dataset. Patterns, right? Patterns filters could be filters. Let's try that. Oof. Okay. Correlate with reduce. All right. All right. I. All right. um, which are literally what filters are. All right. Cool. Wonderful. Correct me if I'm wrong. Right. Lower. I use the word lower because I didn't say correlates with reduced loss across the label dataset, which is lowering the loss. Right. Filters, which are literal the visual correlations statistically, but let's uh let's say I'm wrong. So now we understand specifically reducing loss across the labeled data set and specifically statistical visual correlations, not filters. Oh, I want to understand logic some more. Let's take some time to go over logics and let's see which one helps more, right? Logics. Must feed the activation of artificial neurons in the final layer. That I understand, but I don't understand why it's called logits. Loss function equals stuff. Logit is a function that maps probabilities 0, 1 to R, infinity, negative infinity to positive infinity. 0.5 corresponds to logic of 0. Negative logic corresponds to probability less than 0.5, positive to greater than 0.5. The vector of that a classification model generates, which is then normal. Okay, okay, okay. So, as a raw score the model outputs for each class before any probability conversion. So it's just a number, right? But what class? So for each class, what are the classes? Ah, I see. So apple, orange, receiver, cornerback, class 0, class 1. Classes are defined by the data, not by the logics. Models are the classes. For a two track, does that mean the probability of class 1? No, because logics are not as a logic. So what's actually creating the logic? Applied to the final layers. And layer, from my understanding, is working with those convolution layers or filters, or sorry. What do we want to call it now? Statistical visual correlations. The network extracts features through convolutions. Okay. And this is to me what's important for learning anything, right? If we never would have taken the time to go over convolutions all for the extra 15 minutes yesterday, I wouldn't be able to come here and understand what the layers are, what they're trying to do and accomplish. it just you lose a lot. You lose a lot the more you skip over and don't go back to. So, and this is why we're here again with logic. Yes, I could technically go past this. It may not even be necessary in the future, but why not, right? Why not take the extra 5 to 10 minutes to really understand the topic so that from there, every time you see it moving on forward, you already know how to handle it and how to approach the situation. So the network extracts features through convolutions, polling, etc. Final representation equals a vector. Call it H. A vector is just a direction, right? The last layer has a weight matrix, W, and then bias vector, B, for clay class. Logics equals W, H plus B. That's it. No sophomore. Go. K equals 2, and K row 0 of W contains weight. Ah, okay. Here's it to how to have this for class. So the logic for class I, which is an arbitrary class, is W for row I, B of row I times H. Okay. Okay, okay, okay. Just scores. Okay. After computing H, the final layer does this. No. A logic is not measuring how much the model likes a class in isolation, right? So it's not liking the apple or orange. It's measuring how much the features in H, which we discerned were feature vector. So how much of H align with the pattern for a class relative to the other classes. Relative difference. I see. I see. I see. I see. Comparative evidence, not standalone likelihood. So, so picture of apple and orange. Apple. Deciding between apple and orange. Logic only if orange is 50% and apple 75%. Logic only cares about the 25%. I see. Okay. So it was the percentage that was messing me up there. So what's the point of the softmax? If network output publish directly, finish and finish. Confident. Okay. Suppose during the training, the model gives logits 20 -1 true class equals index 0. Gradient update B larger small. Right. Okay. So extremely confident verse 1. Right. Okay, so now what is the softmax doing? I understand what the logic is doing. Now what is we doing with the softmax? given logits. So we have logits like 200 and then -1 because we're not confident about this one, super confident about this one. It produces probabilities by giving us, okay. So whatever function this is going to be, we're saying this logic 200 gets this function done to it. This logic -1 gets this function done to it. Uh, maxima makes all values positive, amplifies differences between. So amplifies the differences between the logits. Normalized by defining and forces all possibilities. Okay, cool. Class 0 to the loss is small because both logits are high. Well, class 0 to class. I'm gonna go B because you got it wrong, right? So in my opinion, you're supposed to get that negative log, right, function going on. And since you were wrong about the logic, you should be hit with a high loss. Range, probability 0, 1. Some constraint. I see. Tiny gradient with the confidence. I see. Okay. So again, here's my current understanding. Logits start the raw numerical output of confidence, right? After that, a softmax is applied using this formula to kind of normalize, make it all positive, et cetera, with the values. But it really doesn't change necessarily anything about the difference between the two values. From there, you have your probabilities, and you're gonna have a predicted class. So this is apple versus what it is, orange. And if you got it wrong, well, you did, it's gonna be a high loss to correct yourself, and then it's gonna try again. Probabilities, cross attribute, computes the loss from those probabilities. Nice. Student X is a 1. So, moderate. Well, you're wrong. I say extremely large. I want to say extremely large because the highest number, the highest confidence is on something wrong. And we want to punish that as much as possible. I get moderate. I understand why it might be moderate. Um, yep. Okay. I understood why it could be moderate, right? Because this gap of confidence isn't too big. But I wasn't sure how much we want to punish every wrong, right? How badly should we punish that? But I understand now. So we should take that into account. And let's do this one more time. Do that with the true class index. Lowest loss to highest loss. So start with the lowest loss. The true class index is 0, then you have to be right. So, okay. And the highest loss will be easiest next. You're wrong, right? By the biggest number. So C, which will leave us B, the middle, A, B, C. Nice. Cool. So today already, let's take a couple months, right? First of all, start writing a notes section for the day. Let's look into logics. Raw numbers of probability. Loss is determined based probability. Yes, correct. True label. feel like these are the main takeaways that we want to start with at the very least. And now we start the okay. B or A could be wonderful, right? Now they are going to be within the same frame, right? So let's go ahead and go do D because maybe there's a more efficient way. Here's what I'm thinking right now, right? There's going to be two different ways we can do this. One, we can have a frame where we have DB, which is X, and then receiver, which is Y, right? And they're in the same frame. And maybe if we get 100 of these, it would be able to differentiate between receiver and DB easier, right? Than if I had 100 DB pictures and 100 receiver pictures, right? Which one would actually be faster for the model to learn? This is our use case, right? This is what we're actually doing. So why not try this first, right? So bounty box and a label, which I believe I've seen before. It's kind of like you've probably seen those AI videos where it's kind of like this. I don't know why he has half of 1 million, have have an alien's wingspan. Um, but this would be the bounty box there, circling, surrounding the player. So then I could treat this throughout the entirety of the film with operations like, okay, where did the angle change on the slant? What was his deceleration speed on the stop and go, right? His angle of release on the post, etc., etc., etc. Dry type bounding box. Ah, all right. So let's go ahead and start. So this is going to turn into one. Train on photos. Go. What are we doing? X1, Y1, Y X2, Y2, and image coordinates, and class label from other. So how to actually do this and how I'm supposed to do this inside the frames annotation, re- X and Y relative to what, etc., etc. There's a lot there's a lot here to actually be able to understand. Um, Object detection. This, in my opinion, seems to be where I would like to pick up next. We now have an understanding of how we want to move forward, right? Not focused on this yet, because in order to focus on the start, we have to understand who is the receiver, because that will classify the start, which will allow us to then do the actual checks of skill and calculations around there. But today we went over logics. We understand in depth how loss works, what it's for, how it works with gradient descent, understand what softmax is using, and now we know our next step on how, right? So what I'm gonna do here actually is just I don't like doing that. So let's go here, day 4. And this in itself is gonna be the key to day 4. So just gonna cut the stream a little short today because this is gonna be in depth and I want to have the time to actually go over it fully. Um, on my own, I am going to go over logs, right? So I'm probably gonna spend about 15 minutes just going over logs. Actually, let's just do that here, right? Let's just spend 15 more minutes, 13 more minutes, go over logs together, so that tomorrow we can all know, all right, we understand how logs work and everything. To calculate logs. Because my understanding of logarithmic equation is so this is a logarithmic equation. This will be your exponential. So what do we got here? Ask math. You can't go wrong with ask math now, can you? Oh, it can't be done. uh, maybe you can. Laws, logics, stuff like that. Might as well, right? Might as well. More commonly referred to as activations. Okay. Since deep learning networks, we remember we went over deep learning, matrix multiplications, and nonlinearities. The raw output can range from negative infinity to infinity. Since these raw outputs can't directly be interpreted as model scores, we have activation functions that are, which is softmax. We didn't go over sigmoid. Get an input image, predict whether the image is a car or not. What would you commonly want? What's the output? 1. Yep. Either car or not car. Yep. Okay. And that's the okay. That's the part where we want it to either be or not to be, right? But we want to have a way to determine the confidence, right? That probability. So that's why we're able to use the infinite range of numbers, right? So then you normalize the infinite range of logits into afterwards 0 or 1, right? raw outputs the values between 0 and 1. I don't know why it's the 1. Okay. Same with softmax, does the same thing. It's not what we're looking at though. Class entropy loss. Went over this. Conclusion. Okay. I'll be honest, I don't think the understanding of a log is necessarily. I don't think it's absolutely necessary from what I'm seeing. But definitely a good refresher. And if it does come up again later on, I mean, hey, we could always circle back, look back into it, and keep building up our knowledge bank. Alright. But that is it for today. Like I said, today we went over a lot about logits, laws, softmaxing, uh, and we have our future plans now of how exactly we are going to handle our training of the AI for images next. All right. So stay tuned, and I will see you all next time.